Hello everyone and welcome back. In this session, we are going to talk about the Snooping-based cache coherency protocol in details. So without any further ado, let's get to learning. Now during our previous session, we learned about the various states which can be specified with respect to the cache line. Now these are the coherence informations which are to be stored in the respective cache controllers. Thereafter, we came across the different cache coherency protocols, that is, the snooping and directory-based protocol. In this session, we are going to observe and try to understand the working principle of the snooping-based cache coherence protocol. Now let's try and understand the snooping-based protocol with the help of this illustration. Let me demonstrate how the coherency is maintained here throughout. Similar to our example that we used in order to explain the cache coherence problem, here we also have the same variable a initialized to 7 residing inside the main memory. At this point of time, suppose P1 wants to access a. Since P1 doesn't have it in its cache, it will be a compulsory miss. So P1 will generate a read request for a and place it on the shared bus. Now this request is a broadcast request. That means all the other caches will be able to read and understand it because their cache controllers are snooping on the shared bus at all times. Since none of the caches have the variable a in them, therefore, they will simply ignore the request, and finally a will be provided by the main memory itself through the shared bus to the P1's cache. Now once P1 has it, in its cache controller, the coherence information for that particular line which has a, the state will be specified as shared. Similarly, suppose P3 also wants to access a, and now a read request for a will be placed on the bus by P3. At this point, P2 and P4, since they don't have any copy of a, will simply ignore the request. However, P1 has a copy of a present in its cache. But then again, it's in shared state. So instead of providing a to P3, it will ignore the request. Therefore, just to maintain the uniform nature of the protocol, finally a will be provided to P3 by the main memory. Now once P3 acquires a, it will also store the coherence information in its controller for the cache line containing a as shared. Now imagine, at this instance, P1 performs the operation on a, that is, it increments the value of a by 1. For this, the state of the line having a will be promoted from shared to modified. Now if we are using write invalidate variation of snooping-based protocol, the moment P1 updates the value of a, P1 will place an invalidation signal on the bus ordering all the other caches to invalidate their local copies of a. Reading this, the cache controller of P3 will demote the state of cache line having a from shared to invalid. Now if we implement write invalidate write through, this particular modification done by P1 will be propagated to the main memory right away, updating the value of a as 8. And in case we are using write back strategy, the modification will be propagated to the main memory during the next cache replacement. Now let me introduce a very interesting situation to you. Suppose at this point P3 wants to perform its operation on a. That is, it wants to decrement the value of a by 1. Now if you observe closely, P3 does have a in its own cache, but it's in invalid state. So P3 can't really use the value that it has inside its cache. And this situation will be considered as another miss. Now if you remember, when we came across various types of cache misses, we learned the term coherence miss. And we were supposed to learn about this during the discussion of cache coherence. Guess what? This is the session where we have just seen that. That means this particular miss is nothing but the coherence miss. Now let's talk about the write update strategy. In write update, instead of generating an invalidation request, P1, as soon as it updates a, will generate an update request and place it on the shared bus, commanding all the other caches to update their local copies of a. And once all the copies of A are updated, all the different cache controller will specify the states as shared. Now in write update, for write through and write back, similar kind of strategy will be followed as we did in case of write invalidate. Fun fact, the AMD and Intel multiprocessors use variations of Snooping-based Protocol for maintaining cache coherence. So this is how Snooping-based cache coherence protocol works. Alright people, that will be all for this session. I hope now you have a clear understanding of Snooping-based protocol. In the next session, we are going to look into the directory-based protocol. So I hope to see you in the next one. Thank you all for watching.